Today we talk about the banker's algorithm. We have already introduced this algorithm before. It's used for deadlock avoidance. It can be used for resources with single instance and those of multiple instances as well. The algorithm is based on prior information that are provided by processes in the system. That kind of information is basically what we represent here in this algorithm as the max matrix. The max matrix is basically the type of resources and number of instances of each resource a process will be claiming on maximum during its life cycle. Okay? So that's basically a matrix of size n by m, where we have n processes and m type of resources. Okay? Also, for every system, we have number of available resources, different types. We're going to represent them by a vector. The vector is called available. The length of this vector is m, because we have m type of resources. So each entry in this vector determines the number of instances of each type of resource. We're going to see that in a numerical example in a while. We also have a location matrix in which the algorithm records the type and number of instances of resources currently used by each process. That is a location. And the need matrix is basically the difference between max and the allocation matrix, which represents the type and number of instances of resources, okay, type and number of instances of resources that a process can request, okay, in addition to what it has. An example is this. So this is a snapshot of the algorithm at one particular time. The system overall has 10 resources of type A, and it has 5 resources of type B, as well as 7 resources of type C. So this is the total resources available in the system. At one time, we looked at the system, we found that the leftover available resources are 3 of type A, 3 of type B, and 2 of type C. And the rest of the resources are allocated to processes. So we found in this case, for example, in the allocation matrix, that process B0 is using 1 resource of B. In the last case, process P4 is using 2 resources of type C, but none of type A and P. Okay? This is what the process should declare at the very beginning. Okay? At the very beginning. The maximum number of instances of each resource type that it can use during its life cycle. So in this case, P0, declaring that on maximum it will be using 7 instances of A, 5 instances of B, and 3 instances of C. Now you can see that needed is basically the difference between max and allocation. So it's max minus allocation. And for that, we can see that process P0 is using 1 of B, 1 resource of type B, and the needed will be this vector minus this vector. And therefore, it is 7, 4, 3. Okay? The same for the rest. The algorithm, the way it works, continuously checks whether the system is in safe state or not. Okay? So whenever there is a request by a process to get resources from the system, the algorithm will check if given these resources to the process, will the system remain in safe state or no? If it does, then it will allocate these resources, and the result is a new state. If not, then the process either has to wait or sometimes has to be terminated because it's violating one of the important rules that we'll talk about in a while. The question is, what's a safe state? When do we say that the system is in safe state or not? For that, we execute an algorithm called the safety algorithm. This algorithm is basically trying to execute the processes with the available resources in the system, okay, in any order that you can find. If you manage to find an execution sequence for all processes, then we can say the system is in safe state. This is the algorithm for. This is if you are interested in coding it, then you can follow this algorithm to do so. Now, as for the snapshot that we have seen of the system, let's check whether it is in safe state or no. Now, looking at the system, excluding the red color information in here, that's basically the current state of the system. Now, we'll try to execute the processes in the system, trying to execute P0. If we are to execute P0 means we're supposed to allocate P0 all the resources that it needs to finish, okay? So to do so, we will look at the needed resources of the process. In this case, P0 needs 743, okay, this vector of resources. And the available ones in the system are only 332, which is not enough for P0 to be executed. So we can't execute P0. Now we try to execute another process, okay? Trying to execute P1, what it needs in terms of resources, the system has it, okay? Which means we can allocate the needed resources by P1. Having said so, means P1 can finish. And if P1 is finishing, means we can get the resources that were allocated to it and add it to the available one at the time it's finished. So we can assume that P1 is finished, and by that we will get all the resources that it was using, which are basically 2 instances of type A. We will add it to the instances of type A. As a result, we will have 5 instances of type A instead of 3. Okay? Now, having executed P1, we try to execute P2. P2 needs 6 resources of A, which we don't have. So this is the new available in the system. The new available, we have only 5 of A. So we can't execute P2. Now we try to execute P3 then, if we can't execute P2. P3, it needs 1 resource of B, 1 resource of C, and we have more than that. In fact, we have 3 of B and 2 of C, which means we can execute P3. So we'll assume that we given the resources that P3 needed, okay? And by that, P3 finish. Again, having said so, P3 finished means we will get all the resources that P3 was using and add it to the currently available resources. P3 was using 2 instances of A, 1 instance of B, and 1 instance of C. That will be added to what we currently have in here. And you'll assume that P3 is finished. And by that, we get 7, 4, 3. Okay? Now, having 7, 4, 3 resources of types A, B, C, respectively, then now we can execute, we will look at P4 if we can execute it. And we can do that, right? Executing P4, because it only needs 4, 3, 1. And we have 7, 4, 3, much more than what it needs. Again, we're going to do the same thing, assume that's executed. And by that, we will get what it was using at the time it's finished, which are 2 resources of C, adding it to the 3 resources of C that we used to have. And now we have 5 resources of C instead of 3. Now we'll go back to P0, trying to execute it. Okay, it needs 7, 4, 3, and we can do that. We can execute it. At the same time, also, we can execute what? P2 as well, right? Which needs only 6, right? So you can execute any one of them in the order that you want. In this case, we choose to execute what? P2. So executing P2, which needs only 6 resources of A, and we already have more than that, then P2 is finished, and by that we'll get what it was using. It was using 3 of A and 2 of C, and that will be added to the A and C resources. So as a result, we have 10, 4, 7. Finally, we execute P0, which needs 7, 4, 3, and we already have. Okay, executing B0 will get the resource that it was using, which is 1 resource of B, adding it to what we had here, which is 4. And as a result, we have 10, 5, 7, which are the initial resources that the system has. And we managed to execute all processes. So we can say that we have an execution sequence, which is this, P1, P2, P4, P1, P3, P4, P2, P0, Or we, as we seen, we can have P1, P3, P4, P0, P2 as well, okay? So we can say, in conclusion, that the system is in safe state. So that's what we've been doing. Now, processes, they do request resources. And when they request resources, they issue a composite request. So they can request a number of instances of more than one type of resource. And the system is supposed to deal with that. So this algorithm, the way it deals with that, it checks 3 conditions in order. The very first condition, the request should be less than or equal than the needed of that particular process, because it's not supposed to request more than what? Left over for it to request, which is needed, right? If it exceeds needed, then that process violated one important rule. And in that case, the system will terminate the process. Okay, will terminate the process. If not, then we check the second condition. The second condition, the algorithm will check that the request is available in terms of the resources. If it's available, then we proceed to the third test. If not, then the process has to wait. The process has to wait. Now, if it's available, proceeding to the third test, in the third test, what we're trying to do, we will assume that we are allocating the resources to the process. And by that, we will have a new state. Having a new state, we need to check it, whether it is safe or no, by executing the safety algorithm. If it's safe, then we're going to commit the new state, and having it as the new state, the process is given the resources that it needs. Now, this is the algorithm 4, which is easy to implement the way it's written. And in numbers, we can follow up with the same state. So this is the state that we have, which we found out that it is safe, right? We just found out that it's safe, assuming that we have this request. P1 requesting 1 resource of A and 2 resources of C. So we have P1 issuing a request, 1 resource of A and 2 resources of C. The request in a vector format. So this is the number of instances of A, number of instances of B, and number of instances of C type resource. Now, what we need to do, so this is the old state. I have the snapshot on this slide, okay, so that we can see the changes that we need to do to formulate the new state, okay? The very first condition to check is whether request less than or equal to needed of P1, okay? So now this is the request, and this is P1 who's requesting. This is the needed, which is 122. We can see that 102 is less than or equal to 122. So the first condition passed, okay? Now we check the second test. We passed the first test. The second test says, check whether the request is less than or equal to available. Now, what we have in available is the 332. The system has the resources needed by the process. So the request is less than or equal to available. So second test passed, okay? Now the third test. To check the third test, we need to formulate a new state. To formulate a new state, we will assume that the request is granted. And assuming so means the available will be decremented by the request, because we will have less resources if we are granting the request by the process, right? So the previous available is 332. The request is 102. Subtract the available from the request from available. What we get is 230. Clear? Okay. And if this process is given these resources, mean the needed will be also less. Will be less. Okay, the leftover needed for the resource. So previously, the process needed 122. And we just allocated 102. So we're going to subtract this from the previously needed. And the result is 020. Okay? So this is the leftover for the future. And since the process is allocated the new resources, means the current allocation for P1 will be increased. Okay, will be increased by the request. So we're going to add the request to what? to allocation. And by that, the allocation of P1 will be 302. 302. Is it clear? Yep. Subtract the request from needed, subtract it from available, add the request to allocation of that particular process. Now, this is a new state. What we need to do is to execute the safety algorithm, trying to find an execution sequence. So let's try to execute the processes. Can we execute P0? We will look at the needed of P0. Can we execute it? We can't execute it because it needs more than what we have. Can we execute P1? P1 needs 2 resources of B, so we can execute it, right? And if we can execute it, what does that mean? It's finished, right? And if it's finished, then we can say P1 is finished. Okay, so I can't do it in here, okay? I will show you on the slide now how we do that, okay? We were gonna write that, okay, in an exercise now. So what we do, okay, P1 is finished, and by that we have what? We have what it was allocated, which is 302, added to 230. And by that we have 532, okay? And then we try to execute another process and so on, okay? And the same as what we followed just now in the safety algorithm. As a result of that, you'll find that we have an execution sequence, and that execution sequence is basically P1, P3, P4, P0, P2. So if you manage to find an execution sequence in the same way that we just did, okay, then we say that it's safe to grant the request for P1. So P1 is granted the resources that it requested, and we have a new state, which is this state. So this new state, this state is committed, and it is the new state of the system. As an exercise, you can also check other requests, such as 330, requested by P4, or the request 020, requested by B0. Towards the end of the class, I'm gonna do some exercises, okay, with you related to this. So if you are like maybe forgetting what you should do to deal with a request, this is the flow chart telling you what to do. So we have a request. The first test says that request less than or equal to needed. If yes, we proceed to the second test, which is request is less than or equal to available. If yes, we formulate a new state. To formulate a new state, you deduct request from available. We deduct it also from needed, and we add it to the allocation of that particular process. Now, this is a state that we need to check it whether it's safe or no by finding an execution sequence. If you manage to find an execution sequence, then it is a new state, it is committed, and the process is granted the resources. If not, at this point, then the process has to what? Wait, and we roll back to the previous state. Okay, so we didn't consider the state that we're working on as what? A new state. So we don't have a new state. So you can see here also if the process failed the first test, means the process requested more than what it needs. And in that case, it should be terminated. Other than that, it will be what? Waiting. So that was the banker's algorithm. Now, other than that, we also, banker's algorithm for avoidance methods, right? Now, the third method that we can use for a deadlock is called detection and recovery. This is used when the deadlock is not frequently happening in the system, so we don't have to execute all of these algorithms, which is basically time-consuming and so on, right? Instead, we'll just let the system work the way it is, as normal. However, periodically, we're gonna execute a safety algorithm to check whether the system is in safe state or not, to discover whether we have a deadlock situation or not, okay? Which means, in this case, when processes request resources, as long as they are available, the system will just give the resources. We'll just allocate these resources to the processes without checking, okay, as what we did in the banker's algorithm. okay? And that might lead to deadlock situations. So what we do at points of time, periodically, we execute the safety algorithm. Which safety algorithm? Is the same one that we just seen, which means the system is recording, the states, okay, based on the requests that had been changed, but is not executing safety algorithm. It's not trying to find execution sequences before the allocation of what? Requests. Also, we can use the RAG graphs, or another simpler form of the RAG graphs that can be derived from the RAG graphs. It's called the wait for graph. The wait for graph. The wait for graph is basically we changing the graph only to be interested in dependencies between processes, which process is waiting for which process. That's why we call it wait for graph. For example, in this graph, we have P4 requesting a resource that is currently used by P1. It means P4 is waiting for P1 to release the resource. So that's the kind of relation I have. P4 waiting for P1. P1 is requesting a resource which is R1 that is currently used by P2, which means P1 is waiting for P2. P1 is waiting for P2. Okay, and so as a result, what do I have? I have a similar graph. Okay, and this graph now, I can look at it and try to find cycles. So if I find cycles in there, then I have what? Deadlock. Or I would say that the system isn't safe. Okay, so we have a deadlock situation. And when I say that I have a deadlock situation, for example, in this case, okay, I have a cycle here, right? Then the processes who are involved in the deadlock are those appearing in the cycle. So this small cycle having P1, P2, P4, okay, back P1, then the processes involved in the cycle are P1, P2, P4. So this is one deadlock, right? I also have another deadlock. P4, P1, P2, P3, or P1, P2, P3, P4, back to P1. That's another what? Deadlock as well, okay? So you can identify deadlock, okay, and the processes that are involved in the deadlock. And based on that, we need to take an action. So we can detect whether we have a deadlock at any point of time. Also, if we follow the same strategy of the banker's algorithm, by keep recording, okay, keep recording the states of the system, the state of the system, okay, and the changes on the state. Then we can check what? So the same thing in here, the available allocation and request, where request in here represents actually needed. Represents what? Needed, okay? The leftover that can be requested by a process, okay, in this safety algorithm. Then, if we're having a snapshot of the system like this, it shows that the system has 0 available resources at this point of time. All of them are allocated to processes. And we have the allocation in this distribution. We have P1 using 2 of A. We have, for example, P3 using 2 of A, 1 of B, 1 of C, and so, okay? And the needed drift over, needed requests for the processes are mentioned in the request matrix, which we used to call needed before, right? Now, what we need to do, periodically, we will look at the state of the system. Assume that this is the state of the system. What we need to do is to try to find an execution sequence. So do we have an execution sequence here? That's what we don't want you to do. Do not jump to conclusions when you see that the available is 0. Okay? For example, this process P1 doesn't need any more resources to finish, which means I can assume that it's finished. And by that, the available will be 0, 1, 0. The same thing for this process P2. It doesn't need any more resources to finish, which means it will finish with time. I can assume that it's finished, and by that, the system will claim back 3 resources of A and 3 of C. Okay? And then I have 3, 1, 3. by executing B1 and B3, I have 3 of A, 1 of B, and 3 of C. And if I have that, I can execute any one of the leftover processes. Right? So the system is in safe state. However, if you found that the system is not in safe state, then there is a deadlock. So this is the detection part. Okay? We detected that there is a deadlock. What to do next? We need to recover from the deadlock. We will look at that in a while. You can also at home try to check these. Okay? Try to solve these. So this is the algorithm. It's exactly the same as of that of the safety algorithm that you have seen in the banker's algorithm. But however here, instead of request, instead of needed, we call it what? Request, the matrix. So how often do we really execute the detection algorithm, trying to find an execution sequence? We said periodically, right? Periodically means it depends on how frequent this particular kind of system used to have deadlock. Okay? So if you used to have deadlock every week, we're going to execute it maybe less than a week, a little bit, okay, in a time that is less than that, okay? If it's every day, going to execute every day, hours, okay, and so on, right? So it depends on how frequent it really happens. And so what we need to do is also to use a particular algorithm for recovery, as we mentioned, right? And that algorithm varies, okay? One important thing is whether, factor that really depends on the kind of algorithm we're going to use for recovery is whether we have rollback states for processes. For example, we can roll back a process to a particular state of it, okay? Because recovery, when we have a deadlock, it means only one thing. Restart some processes. Because when we restart a process, all resources that were allocated to it will be claimed back by the system, hoping that this will resolve the deadlock. But it might not. It might not. Now, if there are like rollback states of the process, what we can do, we can roll back, okay, in the state of the process. Now, not assuming so, rather than restart it from the very beginning, right? So what we need to do is to terminate processes. One option is to terminate all processes who are involved in a deadlock situation. In fact, to restart them, okay, to restart them, right? Restarting all processes involved in a deadlock, those who are involved in a deadlock, means releasing all the resources that they have been using. And then maybe when they restart again in different order and different, all right, then we might not have what? A deadlock. So we are not doing any algorithm in there, except that we already identified which are the processes involved in deadlock, and that's done already by the detection algorithm. So recovery, one thing. Restart them all, okay? Or, instead of doing so, we only pick up certain processes to restart, hoping that by doing so, we resolve, okay, the deadlock situation. The question is, which processes that we should pick up to restart? One strategy, as your classmate just now mentioned, okay, to choose the process that has the maximum number of resources compared to the others who are involved in a deadlock situation. So the system will be claiming the most resources by only what? Restarting one process. That might happen, okay? So this is the way, a strategy, and the reason behind it, okay? Another way is by using the lowest priority process, because in this case we do care much about what? Higher priority processes, okay? They are much more critical in terms of the work that they are doing. Or we might use the youngest process. Youngest process means the process that just started, okay, or had been executing for the shortest time compared to the rest of the processes, so that the cost is least, okay, in terms of damage. But someone might argue, no, we need to restart the eldest process, because most likely that had been involved in the deadlock, and it is one of the initial causes of the deadlock, as well as it might have the most resources. So you start that. So basically different strategies, and for each there is what? A reasoning. However, if we choose any one of these strategies, for example, let's say that we restart the least priority. Restart the least priority process, hoping that the system will be recovered, right? But, which means we need to check. We need to check after restarting each process whether the system now is in safe state or not, which means we have to execute the safety algorithm. And if it's not, then we have to choose another process, either using the same strategy or different strategy, okay? And again, we have to execute the safety algorithm. It's time consuming. And we might end up that we're doing most of the processes. We are doing the same process for most of the processes to get what? A safe state of the system. That's why most of the time what is chosen is what? Restart the processes. That's much faster. That's much faster. By the time you already find a safe state by restarting one by one, maybe these processes, if we already choose to restart them, they would have finished, okay? So basically, there are questions related to selection of the victim, which victim to select to restart, if we are to choose to restart that way. We need to minimize cost. Cost has many factors, okay? Cost is basically an optimal equation that has many factors. Maybe the time that is needed to resolve what? The time that is needed to resolve the deadlock, right? Or it could be the number of processes that we restart, okay? Or both of them, okay? And many other factors might be involved in there. As we mentioned before, rolling back, returning to some safe state, restarting a process from that state is something also possible if we have that for processes. Now, if we choose one strategy for restarting processes and we stick to it, for example, we always restart lower priority processes, then what we're going to have is starvation. Always the one you're going to choose is the lowest process to restart. So that's why sometimes we can mix up between strategies, okay? The first time I restart a process with lower priority. The second time I restart the youngest process, and so, okay? So that we don't have what? Starvation. Now, towards the end of the presentation for deadlock, I have few exercises for you. Basically, this is a collection of questions that I've been asking students in previous exams, okay? So this is a question that shows you a current state of the system, and you are asked to check a particular request by a process, whether it can be satisfied or no, why, and you need to show your work. To utilize the time perfectly, we have given you formatted, okay, tables, okay, and maybe spaces that you need to do your what? Tests, okay? We also have other questions related to RAG graphs, okay? For example, in this question, you are given a RAG and you are asked to write the allocation matrix. In fact, I can do that using the RAG graph. The allocation matrix is what? Telling which process using what type of resource and how many instances of that resource, correct? So what we have in here, for example, for P1. P1 is using one resource of A, right? So my first row in the allocation matrix will be 1, 0 of B, or there is, in fact, P1 is only using one resource of B and one resource of C. That's the assignment, correct? Visible. Okay, so P1 is using one resource of B and one resource of C. So I can say that the first row of the allocation matrix is 0, 1, 1. Correct? It's not using any resource of A. It's not using, okay? It's not using. Allocation means what it is using, right? And if I am like looking at the second row, which is basically corresponding to P2, then I can say that P2 is currently using one resource of A, but none of B or C. So the second row is 1, 0, 0, and so, okay? Find the available vector. Available vector. I have 2 of A, that's all of what the system has, and all of them are allocated. So what's available way? 0. I have 3 of B, all of them are allocated. And no, 3 of B and they are allocated. So 0 B, right? I have 3 of C, 2 allocated means I'm left with 1, okay? So we can, get that kind of information. You draw the weight for a graph. Basically, you can see that P1 is waiting for P2, right? And it's waiting for P3 as well, right? And so. Is the system in deadlock? We try to find the cycles here or in the weight for a graph. That's easier, okay? And from there, you check. So that's the kind of questions. Now, let me try to solve one with you here. Light is not on. It's supposed to have some light there. Huh? No light, so sorry, you have to live with it this way. Sorry? Yeah, I'm using it. It's not working. Come, if you can help. The light is here. This is the button for it. But if there's any other button, this is the light button. Maybe the light is. So the light is. Sorry. Okay, so this is what we have, okay? And now it says that you have, okay, so you have 7 of A, so I can write here A, 7, and I have 6 of B, B 6, and I have 4 of C, and basically D, I have 8. Right? So this is what the system has overall. Now this is needed. This is current allocation. What I need to do is to try to satisfy this request of P0. And the request says 1 instance of B and 1 instance of D. Okay? So 0 of A, 1, 0, 1. That's the request, okay? Now the first test, I need to check whether this request is less than or equal to needed of what? P0. This is P0 needed. It is 0, 2, 1, 2. So I can say what? 0, 1, 0, 1. Is it less than or equal to? 0, 2, 1, 2. Is it? Why not? It is. Okay, 0 less than 0, 1 less than 2, okay, 0 less than 1, and 1 less than 2. It's a vector, right? Let's say, okay, yes. Okay. Now test 2. Is it less than, okay, 0, 1, 0, 1, is it less than or equal to available? Do I have available? I don't have available calculated yet. Okay, this is what the system has overall at the initial, okay? Initially. So I need to find available. To find available, I need to see what had been assigned out of A. So I can find here that there are 5 of A already assigned. Okay? And here 3 of B. And I have here 4 of C and 4 of D. Okay? Now I can deduct that to find available. Okay? I can deduct it from the initial resources. So 7 minus 5, 2. And 6 minus 3, 3. And basically, I have 0 of C, and I have 4 of B. Right? So this is what I have. Clear? Okay. Now, I can check. So yes, it is, because 0 less than this, 1 less than 3, okay, and so on. So we can check it now to find out that it is really less than what? Available. So the second test passed. Now I need to do the third test. The third test, the way I'm supposed to do it is by formulating a new state, okay? The new state, it is B0 the one that's requesting, right? And this is the request. I have to deduct it from where? From available, okay? And from needed as well, okay? So if I am to deduct it from needed, then instead of this one, what I'm gonna have? 0, right? Okay? And here 1, I will deduct it from D, which is also what? Sorry, I'm talking about, sorry. We're talking about P0, right? Not P1, P0. So I'm gonna deduct 1 from 2, so this is 1. And this one from 2, so here I have what? 1. So the needed now, the new needed of P0 is 0, 1, 1, 1. Okay? Now the allocation of P0, I will add to it the request, right? So I'll be adding 1 of B here, so I will have 1 instead of 0. And I will add 1 to D, so I'll have what? 2. So this is the current allocation of what? P0. Now, yeah, I add to allocation because I'm giving resources to the process, right? And now I deduct this request from available. So available will be what? Deducted. So we said this is available, right? Which means available will be instead of this what? Okay, so we're going to be 2, 2, 0, 3. Okay, let's say so. 2, 2, 0, 3. Okay. Now, I need to check the test, which is whether I can find an execution sequence or no. Let me try to execute processes with the new available. So this is the new available, right? Now, can I execute P0? P0 needs 1, 1, 1. Right? Do I have 1? It needs 0, 1, 1, 1. I don't have. It needs 1 of C, which I don't have. So I cannot. Let me try to execute P1. P1 needs 1 of B and 1 of D. 1 of B, so I have, right? So I'll assume that P1 is executed. And you know, by assuming so, because we already have, then we can get the resources that B1 was using and added it to the system resources. And that is basically 1 of B, 2 of C, 1 of D. So I can say A is not changed, but this one is changed, becomes 3, and this one becomes what? 2, and then 1, this one, 4, right? And I executed P1 already, correct? Now let me try to execute P2. So when I am trying to execute, I will look at needed, okay? At needed, right? Now P2, it needs 2, 4, 0, 2. Do I have 2, 4? I don't have. So I will try to execute P3. So this one already done, right? P3, trying to execute it, I only need 1 of B, 2 of C, which I have. So I'll assume that P3 is executed. And by doing so, I will get the resources that it was using, which are 1, 2, 1, 0. So right? Now let me try to execute P4. P4 needs 2 of A, 2 of C, 2 of D, which I have, right?
So I'll execute P4. So I already executed P3, now I'm going to execute P4. And by that, I will get the resources that it was using, which are one of A and one of D. So I have 4. Okay. Now let me try to execute P0. Okay. So what I do, I check like this and then go up again, okay, and again, and so on. Right? Now, P0, it needs one of B, one of C, and one of D, which I have. So I can execute it, P0. Right? And by executing P0, I will get the resources that it was using, which are 2 of A, 1 of B, 1 of C, 2 of D. Okay, so I'm going to add 2 here, that's 6. I'm going to add 1 here, that's 6. I'm going to add 1 here, that's 4. I'm going to add 2 here, that's 7. Okay? Now let me try to execute the last one, which is P2. P2 needs 2, 4, 0, 2, which I have. So I'm going to execute P2. Okay, and by that I will get the resources that was using, which are 1 of A and 1 of D. So I'm going to add it here. I'm going to add it here, 1 of A and 1 of D, and this is what I have. So by executing them, and I managed to execute them, I can say that the execution sequence is P1, okay, P3, P4, P2, P0, okay, and P2, right? Therefore, what? Therefore, request is granted, and we have a new state. Now, if you want to make sure that your calculations are correct, just in case you're doing the simple mistakes, always check while you get towards the end with what the system initially has. So they are what? Equal. They are equal. Right? So this is one, the type of questions that you will really be asked to. So here, test 3, we're trying to find an execution sequence. But first, we have to formulate a new state. Okay? You can reflect it here, the new state. And if you manage to, then you say that request is granted, and we have a new state. If not, you can say request is not granted, process has to wait, and we don't have a new state. Okay, basically, we just